So in discrete time, one thing we cared about for Markov chains were these various results on the long-term behaviour of the Markov chain. What happens as the time, which then was n, but now is t, as that tends to infinity, what happens? So in discrete time, we looked at stationary distributions, we had a definition, we saw how to find them by solving some simultaneous equations, and we had a theorem on their existence. Then we had this convergence to equilibrium idea, which was governed by the limit theorem. And then we had the ergodic theorem about the long-run proportion of time spent in each state. And so here we're going to develop the same thing for continuous time. We're going to see the definition of a stationary distribution in continuous time and how to find one by solving some equations, some different equations this time, and a theorem about their existence. Then we're going to look at convergence to an equilibrium distribution, and we'll have a limit theorem that tells us about that. And then we're going to look at the ergodic theorem about the long-run proportion of time spent in each state. So everything here will be mostly the same as in discrete time, but there'll be just little differences here and there, which I'm going to try to bring to your attention as we go through. So we're going to start with a stationary distribution for continuous time processes. So let's start with the definition of a stationary distribution, and what we see here is the definition that's the same as the one as we had in discrete time, right? We have our old friend pi equals pi p. In discrete time, obviously we'd be given p at the beginning of a problem, but here we have the transition semigroup p of t, which has to take the place of p in discrete time. So if we have a Markov jump process with a certain state space and a generator matrix and a transition semigroup, then some distribution pi is a stationary distribution if pi j is the sum over I, pi jt for all t and all j, or in matrix vector form if pi equals pi p for all t greater than or equal to 0. So that's the formal definition, same as before, but we've got a t in brackets in there. The problem is that this definition is like a pain to use, right? Because when we're told about a Markov jump process, what we're given is Q, the generator matrix. And so what this definition suggests is that first we have to solve the forward and backward equations, maybe using a matrix exponential to find p of t. Then we have to solve pi equals pi p of t for all t. And this just sounds like a nightmare. And luckily, it's in fact much easier. Because in fact, it turns out that what we can do is just solve pi q equals 0. We can just solve that instead, where here, remember that distributions are row vectors. So 0, by here I mean the row vector of zeros. So, in fact, things are much nicer and we can just solve pi q equals 0. We ought to prove that fact if we're going to use it. So, theorem, let xt be a Markov jump process in continuous time, have generator matrix Q, and if pi is a distribution, as in all the elements are positive or at least non-negative and they add up to 1, with pi q equals 0, or if we want to write it out in component by component form, that's sum over I, pi I, q I j equals 0 for all j, then pi is a stationary distribution. So this is saying that if we solve pi q equals 0, then we do indeed find a stationary distribution. Okay, we can prove this whilst we're here. Why not? So we're going to assume that pi q does equal 0, and we need to show that pi equals pi p for all t. Okay, so this is saying we want pi p of t to equal pi. So the left-hand side here depends on t, but the right-hand side doesn't. So there's this kind of general technique that we use sometimes in maths, which is that if you want to show something with time dependence or dependence on another variable takes on a particular value all the time, we can do this in two separate steps, which is one, show that it's constant, and two, find that constant value. Right. So to show that pi p of t has the constant value pi, well, we could first show that pi p of t is constant, and then show that that constant value is pi. So that's the way we're going to do this. So first step will be to show that pi p of t is constant, as in constant in time, doesn't depend on t. Well, if we've got a function of t and we want to show it's in fact constant, a good way to do that is to show that its derivative is 0, right? If we want to show something is constant, we show that its derivative is 0, and then we know it's constant. So let's differentiate pi p of t and see if we can show the derivative is 0, and therefore that we know it's constant. So what is the derivative? d by dt of pi p of t. Well, pi is just a vector. It's p of t that depends on t, right? So we can take the pi outside the differentiation. There's a slightly minor point here, which is that if the state space is infinite, you have to be a little bit careful with justifying taking something outside the derivative. We're all happy with the derivative of 5 times x is 5 times the derivative of x. But when you've got things in infinite dimension, you have to be a bit careful. I'm not going to be careful in these notes because it is true generally. But if you like, we're only proving it for the finite case. Or if you wanted to prove it for the infinite state space, you do have to just be a little bit careful that that step is allowed. Okay, here we've got a d by dt of pt. And we have some equations that tell us about the derivative of p and t, right? We have the forward equation and the backward equation. The forward equation tells us that p of t, if you differentiate it, is pq, and the backward equation tells us it's qp. What you probably want to do in real life here is try out both of them. Try out the forward equation, try out the backward equation, see if either of them proves the theorem you want. Turns out that on this occasion, it's the backward equation that will do it for us. So if we were to try the forward equation, we'd get a bit stuck, and then we'd try the backward equation would work. And so, because I know the backward equation is the one that works, I'm going to go straight to that. But there's no magic here, right? I could have tried them both, and it would have only taken me another minute or so. So the backward equation says that the derivative of p of t is q p of t. That's the backward equation. Oh, but hey, look what we've got here. We've got this pi q here, and up here we said that pi q equals 0. So all that lot, well, it's 0 times p of t equals 0. So we have indeed shown that the derivative of this thing is 0. So pi p of t is indeed constant. So that is good news. Step 1 done. So shown that pi p of t is constant, we want to find that constant value, and we want to show that constant value is pi. So second step is to find the constant. Well, we know that p of t doesn't depend on t, it's the same for all t. So we could just pick some simple value of t where we know the value, right? Because if we know the value for some t, then the fact it's constant tells us it for all t. So is there a special value of t where we know what the answer is? Well, yes there is. There's t equals 0, where we know what things are going on. So when t equals 0, we have pi p of t equals pi p of 0, just picking our favourite value of t, since we know everything's constant, because we know that pi of 0 equals I, the identity matrix, right? That's the initial condition in the forward and backwards equations, or it's just obvious that in time 0 you don't move, so your transition matrix is I. But if you multiply something by the identity matrix, you just get itself, so that's pi. So pi is indeed the constant value. And hence we have indeed shown that pi p of t equals pi all t. So pi is the stationary distribution. QED. So we have managed to prove that. But the message of all that proof is this thing here, that we just need to solve pi q equals 0 to find a stationary distribution. So let's do an example, shall we, of finding a stationary distribution using this new equation, pi q equals 0. Example. This is an example that we did in one of the previous sections before Easter. I don't know whether you remember this example or not. But the example from the previous case was this. Note that we have negative numbers down the diagonal, positive numbers off the diagonal, and the rows add up to 0, just as it should with a generator matrix. And so we want to solve pi q equals 0 to find a stationary distribution. So all the steps here will be exactly the same as in discrete time. Right. So when we're in discrete time, the first thing we did is that we would write out the equations one by one. Right. So we want pi 1, pi 2, pi 3 of this equation up here to equal the row vector of zeros. So taking that one column of the matrix at a time, in the first column we get minus 2 pi 1 plus pi 2 equals 0. From the second column we get 2 pi 1 minus 3 pi 2 plus pi 3 equals 0. And from the third column we get no lots of pi 1 plus 2 lots of pi 2 minus 1 of pi 3 equals 0. You'll remember in discrete time that it was always the case that we had one more equation than we needed and that we could throw one away. Same is true here. I'm going to throw the middle one away because that looks the most complicated. That has 3 terms in it. The other ones have 2 terms in it. So I think I'm probably going to make my life easier. I pick that one to discard. Okay, what was our second step in discrete time? Our second step in discrete time was to solve in terms of a working variable. And we'll do the same here. Looking at my equations, I see that they both have pi 2 in. So again, I'm going to pick pi 2 as my working variable, just because I think it's going to make my life easier. Again, if you discarded a different equation or picked a different working variable, that's all fine, but I just think this is going to make my life easier. So from the first equation, I get pi 1 equals a half pi 2. Just by taking the pi 2 over to the other, taking the minus 2 pi 1 over to the other side and dividing everything by 2. And from the third equation, just take the pi 3 over to get pi 3 equals 2 pi 2. And thus I have solved in terms of my working variable, pi 2. Third step, again, you'll remember this from discrete time. The third step is that we use a normalizing condition because pi has to be a stationary distribution. It has to be a distribution. So the entries of pi have to add up to 1. Right, so we need pi 1 plus pi 2 plus pi 3 to equal 1. Well, we've just shown that pi 1 equals a half pi 2. Pi 2 is just pi 2. We've just shown that pi 3 equals 2 pi 2. So that all comes to 3.5, 7 over 2 pi 2, and we need that to be 1. So pi 2 equals 2/7. So pi 1 is half that, which is 1/7, and pi 3 equals twice that, which is 4/7. And thus we have our answer that pi equals 1/7, 2/7. 4/7. And that is our stationary distribution because it's a distribution that solves pi q equals 1. Finally, you'll remember that in discrete time we had a theorem about the existence and uniqueness of stationary distributions, and we have a similar theorem here. Again, assume we have an irreducible Markov jump process. Then if we're positive recurrent, then the stationary distribution exists and is unique. It's given by this equation, whereas if we're null recurrent or transient, then we don't have one. So this is almost exactly the same Note that there is a little difference in this expression here. Before we had pi I equals 1 over mu I in discrete time, where mu I was the expected return time. Here there's an extra qi in there. That kind of accounts for the fact that we sit at state I for a certain amount of time before leaving. So that expression there is slightly different. There's just a little extra qi hanging around. But the theorem, which says that if you're irreducible and positive recurrent, then you have a unique stationary distribution, is all the same. So again, that's another thing where everything is almost exactly the same in discrete time, but with just one little change.